Welcome back to the type system. I'm Daniel, and in this video we're going to discuss an advanced Scala feature, which is type refinements and compile time duck typing, which is super interesting for a statically typed language. Now, I think you've gotten a reflex by now. Let's go to the Part 5 type system package and create a new Scala application. Let's call this structural types, or type refinements, or compile time duck typing, or name it whatever you want. Make it an object and make it extend app. Now, in this lesson, we are going to dissect the notion of a type as a structure. So one of the first things that we're going to talk about is structural types. Now, imagine that in your huge team, someone wrote something with Java and Google Guava that you want to use. Now, Java has this interface, which we will write as a trait here, which closes things. And we are going to write this at a type alias. So type Java closable as java.io.closable. Okay, so this is a kind of things that can close. Now, in the meantime, your own team has implemented their own closable in the form of a class. Let's call this hipster closable, with something that has a def close, which is a unit. And this just prints something to the console, like, yeah, I'm closing. Okay, so both of these types, both the Java IO closable and your own hipster closable, have a close method which returns a unit. Now, as a sane programmer, you want to write a method that can safely accept both this guy, the Java closable, and your own hipster closable without duplicating the code. Okay, so let's say you implement something like close quietly, which is a method often used in Guava. And this takes a closable, which is of type either Java closable or hipster closable. Too bad the compiler doesn't allow us to do that, but wouldn't it be nice if we could in some way? Well, the solution here would be to say, let's call this a type alias with the name unified closable, and the type that I'm going to associate with this name is going to be simply open and curly brace and declare a method called close, which returns a unit inside. This thing right over here is called a structural type, and I've just named it unified closable. A structural type may have values and variables and methods inside, and the nice thing about it is that I can now write def close quietly with a unified closable. And let's just say this returns unit, and the implementation is just unified closable dot close. And now I can safely say close quietly for a new Java IO closable. Okay, and I can also say close quietly with a new hipster closable. So now close quietly works fine for both of our types. So even though these two things are completely different and unrelated, they just match the type structure that this method requires, which makes the compiler happy. Now let's use our little weapon with structural types to define what we call type refinements. What do I mean by that? So let's leave a few spaces here, because there's a new example incoming. So I can declare a type, let's call this advanced closable, which is a Java closable, which is in fact a Java IO closable, and then I can simply say curly brace, and I can add a new method here. For example, close silently, which returns unit. So advanced closable is a Java closable plus this little thing, this little method. Okay, so this is enriched, a type refinement we like to call it. Now, I want to show you how this refined type can be substituted with, for example, a class that I write in some other part of my code base. I'm just going to name this advanced Java closable, which extends Java closable, which is basically Java IO closable. So this needs to implement the close method. And let's just print line Java closes. And I also want to add this close silently method, which also returns unit. And let's just print line Java closes silently. So I want to show you how this class that I write in some other part of my codebase is a good substitute for the type alias that I wrote here. So if I define a method, say this close shush, and this receives an advanced closable as this guy, which again is a type refinement, and say this returns unit and simply calls this parameters close silently method, then I can use the close shush method, close shush, with a new advanced Java closable. That's because the compiler figures out, okay, advanced Java closable originates from Java IO closable, and it also has the close silently method, which the refined type here also has. Okay, so the compiler does this type checking for us to make sure that this value here, this instance, has the right type. But if I added the close silently method on my hipster closable, so def close silently, which returns unit and saying print line, for example, not making a sound. Okay, then I would not be able to say close shush with a new hipster closable, because hipster closable does not originate from Java closable, even though it has all the methods. So this is not okay because the compiler is smart to figure out where the type refinements originate from. Okay, so we've learned about structural types and how we can refine existing types with structural types. Now, the next thing that I want to show you is how we can use structural types as their own types, as standalone types. For example, if I write a method, let's call this alternative close, which receives a closable, and here's what I'm about to write. Open and close curly brace and simply saying def close unit. So this guy right over here is its own type. And if I implement this as closable close, then this is a valid method definition. So what I wanted to show you is that this little thing is its own type, which makes sense because originally when we created the unified closable, we aliased it with this guy, which is its own type. Okay? So we learned how to define structural types, refine existing types with structural types, and use structural types as standalone types. Cool. Now, let's look at these structural types in the context of the compiler type checking. And we'll see a mechanism known as duck typing. Python programmers may know what I'm talking about. So say, for example, I have a little type called sound maker, which is the type of a thing that has a method called make sound, which simply returns unit. And let's say I have two very different things. I have a class dog, which has a make sound method, which returns unit and just prints line, say bark, and also a class called car, which has a method called make sound, which returns unit, and this just prints line, for example, vroom, sound of an engine. Okay, now from a structural standpoint, Dog and car both conform to the structure defined by SoundMaker. So from the compiler's point of view, I can safely say val dog defined as a SoundMaker equals, and on the right hand side I'm going to say new dog. And a car of the same type SoundMaker equals new car. So the compiler is fine with all of these as long as the types on the right hand side conform to the structure defined on the type of the left hand side. This is called static duck typing. JavaScript programmers and Python programmers may be very well familiar with what is called the duck test, which says something like, if something looks like a duck and swims like a duck and flies like a duck, then I can treat that something as a duck. Meaning that if an instance conforms to the structure defined by some type, in this case SoundMaker, then I can use it as an instance of that type. So a new dog can be used as a SoundMaker. The process is called duck typing by the duck test and is usually present in dynamic languages like Python and JavaScript. The Scala compiler is smart enough to do the duck typing test at compile time. So this is super cool, with one big caveat. The structural types, including the type refinements, are based on reflection. That's how the Scala compiler is able to guarantee at compile time that an instance will be used as a structural type, because at runtime, the program will inspect the presence of the makeSound method and it will invoke that at runtime. Now, if you're an advanced JVM or Java developer, you know that reflective calls have a big impact on performance. So only use structural types when you absolutely need to. If you take a look at the IDE hints here, you see that we have a little tooltip saying advanced language feature reflective call. So our structural type definitions are all based on reflection. Now, let's test what we've learned with two small and simple exercises. Let's say we have a simple trait called CBL from consBase list. Okay, so this is the general trait of a list with a def head and tail. Okay? And totally unrelated, I'm going to have a class human and a class brain. Okay? And the human class will have a def head method which will return a brain equals new brain. And the brain just has, for example, a toString method. So toString, just override that and saying brains. Okay, so we have a consBase list with a head and a tail, and a human with a head, which returns a brain. Okay, all right. Given that, I'm defining a method called f, and I'm going to parameterize that with a type t, and I'm going to pass in a structural type as parameter. So I'm going to name this something with a head with the type structural type, and inside I'm going to put in a def head which returns a t. And this just returns unit and just prints line this argument's head. Okay? So I wrote this little method. My question to you is, try to think of, without running the code, whether f is compatible with a consBase list and with a human. So this was the first exercise. The second exercise is also an exercise in compatibility, and I'm going to define a small object, and I'm going to name this head equalizer. Inside, I'm going to define a type alias called headable with a type parameter, which is a structural type with a method called head, which returns a t. If in any case you're wondering whether type members can also have generic types themselves, yes they can, don't be so shocked. Okay, and let's say this head equalizer thing has a def triple equals, which takes a type as a parameter and compares two headables, A, which is a headable T, and B, which is a headable T. And this returns a Boolean, and the implementation is simply a head equals B head. Just calling the head method. Okay? Again, without running the code or without doing examples, I want you to think whether this head equalizer is compatible with a cons-based list and a human. Okay? So pause the video, think about how you would prove that, and I'm coming with some examples. If these just happen to not be compatible with a cons-based list and with a human, think of why, and again, with examples. Before I actually go though, I should make a correction. This head method doesn't take parentheses. I've added them in my little reflex, but the head method is only an accessor. This is actually important, okay? So having done that, feel free to pause the video and get on with the exercises. So, what do you need to do to make f, this guy, compatible with a human and with a cons-based list? And the answer is nothing, because f is compatible with both. So say, for example, that I have a super quick implementation of this cons-based list with a case object cb_nil, which extends cbl nothing. And let's implement these methods real quick. So def head is nothing equals question marks, and tail is also cbl nothing, and this is question marks. And also a case class concrete or cbcons with an override val head of type T with a type parameter in place, and override val tail, which is a cblt. This extends cblt. Okay, so having defined that, a super quick implementation, I can simply call f with a new or a cbcons with, say, 2 and cb_nil. So this is fine because the cbcons has the head accessor in place, which conforms to the structure that the parameter has. But f is also compatible with a new human. And this is very interesting because, as you see, the f method is typed with a type parameter t, and you may wonder, what is the type parameter t? Now, the compiler is smart enough to figure out that the type t is actually brain, which is super cool. Cool, so let's go to exercise number 2. Is this head equalizer dot triple equal compatible with a CBL and with a human? The answer is yes. So, if I define, let's call this a brains list, equals new or cbcons with a new brain and a cb_nil. Alright, so a list of brains. Then we can safely say head equalizer dot triple equals between a brains list and a human. So I'm just going to call this new human. So this is fine. But this also poses a problem, because I can say, let's call this val strings list equals cbcons with, say, brains, the string, and cb_nil. And I can say head equalizer dot triple equals between human and strings list, so the new human, and strings list. So this is also possible. which is wrong because while in the first example both the head method applied to the arguments returned a brain, in the second case the head for the first argument returns a brain and the head for the second argument returns a string, which is wrong. So not type safe. Now you may wonder why this happens. Well, it happens because the structural equalization here, the implementation here, relies on reflection. Now, because this all relies on reflection, the compiler is able to erase the type parameter t here, which basically reduces the triple equals method between a headable and another headable, which both a human and a string list are. But this is also wrong and not what we want. So I want you to be very careful when using structural types in the context of methods with type parameters. Alright, so in this lesson we've learned some powerful Scala features, but like all things powerful, they should be used responsibly. I'm Daniel, and I will see you in the next video.